Hello again. So let's just continue our journey of documenting this book reading. Um, right now, I have read some part of chapter 2. I also recorded it, but eventually the recording was not that much useful. Uh, I was not able to record my browser or even the book. There was some issue, right? So I have read these pages. I have read, and let me go the page from where I have to start reading. Uh, I guess yes. Yeah, I was here last time. I have read the till here. So let me just open up my browser and have a notebook. Yeah. So what I we have learned till here from chapter 2 is that we have seen some basic uh, operations which we can perform using the tensors, and also why tensors are preferred over numpy arrays. There is, I have covered this. Now I'm trying to train or build a simple neural network using pytorch. Okay, and have written some code. So this is the code. The This is the main part of whatever I have written till now. This is the main chunk or piece of code. What I am doing here, that I am initializing a class, and I am also inheriting the nn dot module, the module class from PyTorch, and there are basically I am training or modeling a very simple architecture in which there are like, let me open up Accelerador. I will be able to. So this is the neural network, or this is the architecture which we are building right here. It has two input neurons and eight hidden neurons and one output neuron, right? As you can see, it's quite easy. And if we want to check weights of any layer, so we can do something like this: the name of the model and the name of the layer and the dot weight. Okay, cool. So yeah, let's just start reading. Now, the values in your output. Okay, this is not that much important. If you want to maintain reproducibility, so you should set manual seed equal to some constant value. In this case, they have taken 0. Okay, all the parameters of a neural network can be obtained by using this following code. This, have I tried this? Yes, no. I can try. I can try. I should try. So print. Uh, Wait. My net dot parameters. So here I'm able to see that something like this is coming. And what is this? The preceding codes returns a generator object. Okay. And what is a generator object? Let's ask ChatGPT about this. What is a generator object? And hmm, these small and silly doubts are important, in my opinion. That's my personal opinion. Some people think that if it's working, then let it work. Not go into depth of it, but I like questioning everything. So a generator object in Python is a type of iterable that is easily generate a sequence of values. Okay. Unlike list, which stores all element in memory, a generate computes each value on demand, making it, so this is something interesting, making it more memory efficient, especially for large databases. Also, it is something like will only work when called. Otherwise, it won't store itself in the memory. It's not called. Something like it. I'll dig deeper into it. So, yeah, I like it. This can be asked if, if someone wants to know that whether I know PyTorch genuinely or not, one should ask this, that what this returns. Okay, but this can be googled up. But one should give a digestible answer. Okay. Finally, the parameters are obtained by looping through the generator as follows. Okay, but in reality, I want actual parameters. I don't want this generator object. How I can get those values for params in net parameters and uh, I think mistakes would kill me, would take my job. Parameters coming, parameter containing this. Okay, great. Yeah, this is kind of cool, right? Yeah, that's cool. The model has registered these tensors as special objects that are necessary to keep track of both forward and backward propagation. When defining any NN layers in the init method, it will automatically create corresponding tensors and simultaneously register them. You can also manually register these parameters using NN.parameter function. Hence, the following code is equivalent to the neural network class we defined previously. Okay. Okay, so this code is similar to the NN.linear one. An alternative way of defining the model using NN.parameter function is as follows. Okay, cool. Uh-huh. So this is more intuitive. This is more intuitive, or this makes much more sense to me, because here we are doing something matrix multiplication and all sort of that stuff. Whereas I'm not able to get idea what I'm doing here, right? But still, that's fine. Uh, this is more clean. I should know that these are similar things. Okay. Define the loss function that we optimize for. Given that we are predicting for continuous output, we'll optimize for mean squared error. Okay. So let's just define loss function now. Function and then dot se loss. Other prominent loss functions are as follows: cross entropy for multinomial classification, binary cross entropy for binary classification. The loss value of a neural network can be calculated by passing the input value to the neural network object and then calculating MSE loss for the given inputs. The loss value for a neural network can be calculated by passing the input values to the neural network object, then calculating MSE loss for the given inputs. Uh, cool, cool. Okay, so let's just do this. Let's say y hat is equal to y net x, okay, and here the loss value equal to loss function and y hat or y. And what one should you should have asked that what would be the values, or we are training this model or we are creating this model, but what is our data? So here, what is our objective is that we will be having two inputs and we want to predict their sum. Okay. So summation of 1 and 2 would be 3, summation on 3 and 4 would be 7, 5 and 6 would be 11, 7 and 8 would be 15. So this is what we want to achieve. Yeah. So let's calculate the loss value for this. And I print it also. Yeah. Loss value. The loss is coming out to be this. Since model is not trained, model we have just initialized the model with random weights. That is why this is happening. Cool. Now let's move forward. In the preceding code, my netx calculates the output values when the input is passed through the neural network. Furthermore, the loss function calculates the MAC loss value corresponding to the prediction of neural network and the actual values. Uh, as a convention, we will use this to associate a prediction corresponding to ground truth. Okay. Also note that when computing loss, we always send the prediction first and the ground truth. Okay, so this is important. I was not aware about this. So this thing is important that when computing the loss, you always send the prediction first and the ground truth afterwards. Okay. I guess I should paste that here. It's quite important, right? Yeah. Cool. The input to the optimizer. Oh, yeah. Now that we have defined the loss function, we will define the optimizer that tries to reduce the loss value. The input to the optimizer will be the parameters, weights and biases corresponding to the neural network and the learning rate when updating the weights. Okay. For this instance, we will consider the stochastic gradient descent. They will more on different optimizers and then impact in next. Okay. Import this method from this and then pass neural network object and learning rate parameters to it. From dot optimizer code std and now if user is equal to std uh, mynet dot parameters learning rate will be equal to 0.001. Perform all the steps to be done in an epoch together. Calculate the loss values corresponding to the given input and output, calculate the gradient corresponding to each parameter, update the parameter values based on learning rate and gradient of each parameter. Once the weights are updated, ensure that the gradients that have been calculated in the previous step are flushed before calculating the gradients in the next one. Okay, so if I have updated my weights, now I have to ensure that the gradients which were calculated for those weights, they should be flushed so that I can again calculate gradient for these new updated weights. Okay, yeah, I got it. Only for illustration. Okay, so as I flushed the previous epoch's gradient, and now what I'm doing is that loss value is equal to this computing loss. Okay, loss value dot backward from back propagation and dot sum. Update the weights according to the gradient. Repeat the preceding step as many as the number of epochs using a for loop. In the following example, we perform weight update process for a total of 50 epochs. Furthermore, we store the loss value in each epoch in the list loss history. Okay, okay. Let's just do this. Loss history for this in range 50. First of all, I'll say op dot 0 that loss value equal to loss function. uh, Loss function output. We define output as my net x y loss value dot code optimizer dot step. This optimizer dot step will update the weights according to the gradient. So I'm updating the weights. Okay, and I'm performing back propagation here. Okay, cool. Optimizer dot step, and what I'll do is this loss history dot trend loss value dot. Cool. Uh, I'm appending the values of this. Let's plot the variation in loss over increasing epochs as we saw in the previous chapter. Okay, cool. So let's just do this. I should probably remove this. Yeah, cool. Run. Cool. Port matplotlib dot pyplot as LT. Let's go. Uh, let's plot this LT dot of streak LT dot next level. I don't like labeling graphs. Bit lazy in this box. LT dot by label value loss variation over increasing box. Okay, let it be. Uh, yeah. So you can see that it has nearly reached zero. Okay. Now let's just try to have some things. Yeah, picked my net. Uh, my net. Let's just give it number 3 and predict. Okay, it must be a tensor, not laced. Okay, dot dot tensor. Hmm, that is nice. Expected all tensors to be on the same device, but found at least two devices. That's so. An important lesson here is that we should always check where. Just give me a second. to dot device. Let's just take this out. Okay. Okay. This. So yeah, it is able to predict. It is able to nearly predict that it would be equal to 5. Okay. Even when it's not in the input data. So this is the beauty of neural networks. Okay. 2 comma 3 is not in the input data, but still it's giving me near my answer. It's because it is generalizing, right? So let's take 1 comma 2. I'm quite sure that it will give me the exact answer. Oh, oh, that I'm shocked. Should have given me exactly E for 1 comma 2. Let's take 7.8 and then I'll move. So this process is called inferencing. Now here we are using the model to make predictions on unseen data or on new data. Okay, close enough. So let's move forward. Note, as expected, the loss value decreases over increasing epochs. Get it wrong. So far in this section, we have updated the weights of a neural network by calculating loss based on all the data points provided in the input data set. In the next section, we will learn about the advantage of using only a sample of input data points per weight update. Okay, we will learn about the advantage using only a sample of input data points per weight update. Okay, need to learn about this. So I'm guessing that here the author wants to talk about the batch size and that and stuff related to. Okay, cool. Data set, data loader, and batch size. One hyperparameter in a neural network that we have not considered yet is batch size. The batch size refers to the number of data points considered calculate the loss value or update weights. This hypermeter especially comes in handy in scenarios where there are millions of data points and using all of them for one instance of a weight update is not okay. As memory is not available to hold so much information, in addition, a sample can be representative enough of the data. Yeah, sure. The batch size helps ensure that we fetch multiple samples of data that are representative enough, but not necessarily 100% representative of the total data. So there are some pros and cons of using batch size. Right. In this section, we'll come up with a way to specify the batch size to be considered when calculating the gradient of weights and to update the weights, which are in turn used to calculate the updated loss value. In the section, we'll come up with a way to specify this. Okay. Okay, so a method which helps us to deal with data sets, custom data sets also. So the data converted into floating point numbers and registered them to a device. Return. Within the my dataset class, we store the information to fetch one data point at a time so that a batch of data points can be bundled together using data loader and sent through one forward and one back propagation to update the weight. So this is actually nice. Yeah. This tells about the full size of the dataset. Finally, the get item method used to fetch a specific row. Okay. In the preceding code, ix refers to the index of the row that is to be fetched from the dataset. It will be an integer between 0 and length of dataset. Okay. Pass the dataset is defined previously data loader to fetch the batch size, number of data points from the original input and out. In addition, in the preceding code, we also specify that we fetch a random sample by mentioning that shuffle equal to of two data points by mentioning batch size equal to 2 from original input data set. To fetch batches from D1, DL. Okay, so this is DL. DL stands for data loader. We loop through it. Okay, this results in the following output. Uh-huh. Yeah, that is good. That is good. Let me code it up. I'll code it on time. Let me read it first. First, kind of right intuitive sense for this. So let's just read for now. Points when the batch size that was specified was 2. Okay, yeah. Now we defined in the previous section that the same finally loop two batches of data points to as just like we. So this is quite important. Okay. While the preceding code seems very similar to the code that we went, and where is if you will read this code, you should be able to recognize that this all means just the addition of this line, right? It just means this. You should read it and you'll understand it. At least I'm able to make sense out of it, so that's fine. The previous section, we learned how to fit a model on known data points. In this section, we will learn how to leverage the forward movement defined in the trained myset model from previous section to predict on unseen data points. We will continue from the code build in previous section. So let's just implement this. Where was I? I need to call out this. So from torch. Fuck this. This. Huh, this. Fuck, this was not. Yeah. So from torch dot hills dot data import data set and data total, right? Uh, I have done this, and this has also been implemented. Now let's create a custom class. Right? So editing our class data set, and now what we are going to do is that tab which self by self dot launch dot self x dot row self dot y would be equal to launch dot insert y dot root. We are specifying the length of the input data class. We have self run self dot if it what this means now is it is used to fetch a specific row. Okay. Um, dot side so the preceding code ix refers to the index. Okay, understandable. No worries. And I can say that I say code of this data model. Yes, size. Let's say two. Let's just try to loop through it. So it is. What is this? Uh, I have no idea why I'm getting this warning. It's okay. Since I have here already initialized it, this so seems like that is why this error is coming. Hmm, But what can I do is that just comment it out. Pardon me. Now I hope this warning won't come. Yeah. Cool. Um. Everything is so far so good. Yeah. And bye. Yeah. Two batches. Fine. I'll need a batch size of six. It's what happened. Batch size is like then what is actually present, right? is still giving the right. We do one thing. Let me say that batch size is 6. Yeah. See, if I define a batch size like this, but I have this number of data points and that, then the batch size will be equal to the number of data points present. Yeah, fine. Mm, Results. The preceding code results in two sets of input output pair. Yeah, fine. That is exactly same. No change in that. That's why I have copied this again. Um, it's different. Take this as model. Why? Uh, put that I have not. It's just uncommented. The time me. Let me switch on my GPU. Oh no, that's yeah. I think I like Kaggle. Yeah, Kaggle is good. Now loss function. I can say that I see loss measure is equal to SGD, strict gradient descent model dot parameters learning rate is equal to 0, 0, 1. Okay, for time equal loss history with this start is equal to time dot time or then the so we are running it for 50 epochs. Okay. For the data loader comma y measure dot 0 grad loss value would be equal to loss function and let this model here. Just give me a second. Output is equal to output by loss value dot dot step loss dot step loss dot time and start. how they are trying to do inferencing. In the previous section, we learned how to fit a model on the known data points. In this section, we will learn how to leverage the forward method defined in the train minet model. From the previous section to predict on unseen data points, we will continue from the code building from the previous section. Okay, what happened? Did all what? Okay, so for now, uh, it's just run everything on CPU itself. No, yeah. So let's say that put like this 10.11. Now we'll do this new input. Say so I will convert it into answer or load. I'm not converting it to device. Okay. Um, yeah. Now let's say output. Let's just check what would be the output. Uh, print out. Yeah, it's nearly equal to 20. The preceding code returns the predicted output values associated with the input data point. So far, we have been able to train our neural network to map an input with the output, where we updated weight values by performing back propagation to minimize the loss value, which is calculated using a predefined loss function. In the next section, we'll learn about building a custom loss function instead of using a predefined loss function. Ah, that is cool. That is cool. Implementing a custom loss function. This is quite important and cool. Certain cases we might have to implement a loss function that is customized to the problem we are solving, especially in complex use cases involving object detection, scans. pytorch provides the functionality for us to build a custom loss function by writing a function of our own. In this section, we will implement a custom loss function that does the same job as that of MSC loss function that comes pre-built within this module, nn.module. Okay, importing everything is happening just like it was happening in the previous section. So there's nothing new. Yeah, define the custom loss function by taking two tensor object as input, taking their difference, squaring them up, and then returning the mean value of this. Okay. So they have just written here uh, the mean squared f mean squared error. I will say y hat because it makes much more sense to me finding it as y hat square. Loss is equal. Now what I can do is that already find this. Yeah. So let's take this. This is coming right. Similarly, the output of the loss value when we use function and we define in step two. Now let's just try to print the value using this. model X. That is same. Voila. Okay, fine. I guess I can remove this. And let's see what happens. This. I'm taking the tensor object. That is it. The final happening here. Uh, I've used as compared to it. We can define a depending upon the problem we are solving. So far, we have learned about calculating output at the last layer. The intermediate layer values have been a black box so far. The next section, we will learn how to fetch intermediate layer values. Okay, so in this, we have to just like mathematically define what will be our loss, and then we have to set it up in our training, right? Okay. Yes. So we'll have to define our loss value. Let's say we have initialized or defined our loss function here, custom loss function here. Then here we will uh, define it up, call it, then we'll do whatever we do with the pre-built loss functions of pytorch. Cool, cool, cool. Yeah, this piece of code was important, and yeah, that was it. This was cool. I liked it. Uh, Fetching the values of intermediate layers. In certain scenarios, it is helpful to fetch intermediate layer values of neural network. Yes, I know. PyTorch provides the functionality to fetch intermediate values of the neural network in two ways. One way is by directly calling layers as if they are functions. This can be done as follows: input to hidden model dot input to hidden x. Okay, hidden activation is equal to mynet hidden layer activation. Note that we have to call the input to hidden layer activation prior to calling uh, input as the output of is the okay, yeah, cool, fine. The other way is by specifying the layers that we want to look at in the forward method. Let's look at the hidden layer values of the activation for the model we have been working. The following code remains same as what we saw in the previous section. We have ensured that the forward method returns not only output but also hidden layer values after activation too. Okay. Oh, okay. We can now access the hidden layer values by specifying the okay. So this is kind of more easy, I would say, right? Yes. Yeah. Using the sequential method to build a neural network. So far, we have learned how to implement a neural network using the class of neural networks where we manually build each layer. However, unless we are building a complicated network, these steps to build a neural network are straightforward, where we specify the layers and the sequence with which layers are to be stacked. Let's move on and learn about the simplified way of defining the neural network architecture using sequential class. However, unless we are building a complicated network, the steps to build are straightforward. Okay, okay, but this is a nice method, right? Even to call a simple, this is good. Let's learn about this. This might also be important in defining our data set and this all this. Okay, yeah, yeah, no issue. Find the model architecture using sequential method available in the NN package. model is equal to this. Okay, so before we were initializing a class, we were calling a class and an dot module for making a model. We were creating a feed forward propagation network and all this. But in using an dot sequential, we don't have to create a class. Okay, so this is quite simple, and it's quite similar to that Keras thing, right? Okay, note that in the preceding code, we defined the same architecture of network as we defined in the previous sections, but we defined it differently. Linear accepts two-dimensional input and gives an eight-dimensional output for each data point. Furthermore, NN.real forms ReLU activation on top of eight-dimensional output. And finally, the eight-dimensional input gives a one-dimensional output, which in our case is the output of addition of two inputs using the final NN.linear layer. In the summary of the model we defined in step 5. Install and import the packages that enables. Okay, so let's try to do this. Summary of which, okay, expects the name of the model and also in order. Okay, the preceding code gives the following output. Let's do this for custom class, custom model. Sorry, yeah, it's not being installed. So what I'll do is, what was that? So uh, take some time. Yeah, has been installed. Fine. Now I want summary of my model. Name is model, but let me check the size, input size of my model. Has one row and two columns. So yeah, that is fine. Hmm. Okay. Seems like it only works for sequential, but let me check. Expected all tensors to be on same device, but found at least CPU and Q. Uh, for this, let me check if I have ever done dot to device. And let me comment it up. And the code again, you expect it to work fine this time without changing the code. Session is session will you start. So this is exactly why I hate Kaggle notebooks. I do love them, but sometimes I hate them. But they are yet still far more better than Google Colab. That's what I think. And yeah, yes, we have entered the summary for our model. We have done that. Cool. So let's try to make sense out of it. If it's -1, then I guess it means that here it's none or there's nothing. And first of all, we have one input or one layer, and then we have internally eight, right? But we have, I guess, two. That is quite using the summary of model, which affects the name of model and also input size of the model. Okay. The preceding code gives the following output parameter 24.9. Okay, so parameter is fine, but I am getting somewhat different output here -1, 1, 8. Here they are getting some different. I'll debug it. Need to check what I am doing wrong. And the only difference here is that they have called this for this one, right? Let's just try and call for this one. And then do the device. See what's the difference here. Uh, I'm passing something like this here. So, seems like an error. Uh, this is some issue, small issue, not a big deal. But I'm receiving the same architecture summary for when I call the model with any dot sequential, and when I call the model with my with like this using this one class one. Okay, so that is not an issue. So, oh, okay. Cool. Not that we have learned to leverage the sequential method to define it. Let's learn about saving and loading a model to make an inference. So this is fine, right? We have not done anything different. We have just added this thing. Okay, and move on to another topic, which is saving and loading a PyTorch model. One of the most important aspects of working on neural network models is to save and load back the model after training. Think of a scenario where you have to make inferences from an already trained model. You would load the trained model side off instead of training it again. Yeah, sure. Before going through the relevant commands to do that, taking the preceding example as a case, let's understand the what the important components that completely define a neural network are. In the following: a unique name for each tensor parameter, the logic to connect every tensor in the network with one or the other, and the values of each tensor. The first point is taken care during the init phase of a definition. The second point is taken care during the forward method definition. By default, values in a tensor are randomly initialized during the init phase, but what we want is to load a specific set of weights or values that were obtained that we learned while training and associate each of those values with a specific name. This is what you obtain by calling a special method described in the following section, and that special method is nothing but model.statement. Okay, so let me highlight it. And the dictionary in this model.static corresponds the parameter names, keys, and the values, weights and bias values, numerical values corresponding to the model. Okay, and model.state refers to the current snapshot of the model. Okay, it returns a dictionary set of keys and values. Okay, let me try it out. Model.state, model.state, right? Uh, okay, let me zoom it a little bit so that it is visible to you all clearly. Right. So you can see that 0 to 8, this is the key, and these are the values for this key. This is the key, these are the values for this key. Okay, these are the names of models layers. The value corresponds to the weights of these layers. Now, how I can save a model? Running save model.static and my model.pth will save this model the Python serialized format on the disk with name my model.pth. A good practice is to transfer the model to the CPU for calling this, as this will save tensors as CPU tensors and not as CUDA tensors. This will help in loading model onto any machine whether it contains CUDA capabilities or not. Okay. Okay, so there are two main learnings from here from how to save a model. First, we can call this function. You don't have to remember it, but a good thing which you should know or you should keep in mind is that you should transfer the model to CPU or model weights to CPU before calling dot save. So this is the thing. Okay. So let's try to save this model. Dot save model dot to CPU dot state picked and name this model as simple model or simple yet complicated. I'm talking about model, not anything else. Okay, we have saved the model. Let's check if it has been saved or not. So this is our output directory. Yes, it is saved. It's saved here. Can I download it? Yes, it has been downloaded. So yeah, it is working. This code works. Now how I can load a model? Want to load it? Yeah. Let's say this is the path. This is yeah. This is assume that this is a new notebook. I have not implemented this, and I have loaded my model. So first of all, what we'll have to do is that create an empty model with the same command that was used originally when training. Okay, okay. Load the model from disk and unserialize it to create an unordered picked value. Okay, this is a little bit complicated, right? At least I am finding it. Static. Let's check it out. Dot load. Okay, model dot load state picked state. Print model. Yeah, model has been loaded, right? So if you have some time issues or you want to save your model easily, you can also use this thing, but they have said that more convenient within a few steps, but it is not advised. Okay. Oh, and so we have finished chapter 2 also. Only 16 chapters remaining now. Yeah. Hmm, let's read summary. In this chapter, we learned about the building blocks of pytorch, tensor objects, and performing various operations on top of them. We proceeded further by building a neural network on toy dataset, where we started by building a class that initializes the feed-forward architecture, fetching data points from the dataset by specifying batch size and defining the loss function and the optimizer, looping through multiple epochs. Finally, we also learned about defining custom loss functions to optimize a metric of choice and leveraging the sequential method to simplify the process of defining the network architecture. Although I liked the normal one, the calling models from class one. All these steps form the foundation of building a neural network, which will be leveraged multiple times in various use cases that we will build in the subsequent chapters. With this knowledge at various components of building a neural network using PyTorch, we will proceed to the next chapter where we will learn about various practical aspects of dealing with the hyperparameters of neural network on image data sets. Okay, questions. Okay, why should we convert integer inputs into float values during training? Because weights would be into float and bias would also be float. We would be calculating differentials. Okay, what are the methods used to reshape a tensor object? I guess dots dot view, dots dot size. Why is computational faster with tensor objects than with NumPy array? GPU parallelize and that sort of thing. What constitutes the init magic function in a neural network class? Anin dot module. It brings all the functionalities of anin dot module. Also, why do we perform zero gradient before performing backpropagation? So that we can clear up the old one, old gradients, so that we can clear up the old gradients. Okay. What magic function constitutes the dataset class? Okay, that is understandable. How do we make predictions on new data points? Inferencing, I have already done that. How do we fetch the intermediate layer values of a neural network? Okay, so by calling out the name of that layer and then dot weight. Okay. How does the sequential method help to simplify the definition of architecture of a neural network? How does the sequential method help to simplify? Okay, so we don't have to initialize a class and then other things. While updating loss history, we append loss dot item. Okay, so this is good. What does this accomplish and why is this useful to append loss dot item instead of just loss? So this is a good question. And I was thinking while I was coding it up, but I know the answer is the thing. I don't know the exact answer of it, but yeah, I just know that uh, loss is some another object of PyTorch and all that shit, right? So I can print it up, loss value. Okay. So like the tensor object, right? And it converts it into integer or something, sort of like that. Let's just check this. Print type cross, and I go through this. Yeah, see, that is the difference, right? Just wrote. So what are the advantages of using this? Okay, so maps, everything. Cool. So that's it for this video. Now I'll start reading chapter number 3 after some time. Okay, so this looks kind of fun. I wanted to study this only. Yeah, yes, yes. I'll enjoy this.